Hello, everyone. My name is Andrei Costin, and I am the CEO and co-founder of Binare IO. And it is my great pleasure to welcome you tonight for our first ever webinar, where we will be introducing firmware analysis monitoring platform by Binare IO. But more importantly, we will summarize the cybersecurity month that has just ended. We'll introduce some new interesting ideas, but mainly we'll discuss firmware security from a general perspective. Just to give you an idea, what is firmware security about and why it is important. This is the first time we do a live, so I expect demo gods to have some influence. But I hope everything goes smooth, and in case there is any problem with audio or video, please don't hesitate. Okay, so let me resume from here because I started hearing my echo. Again, apologies for any hiccups in this live session. Okay, so let me start by introducing some motivating examples about why firmware security is very important and where firmware security has failed us so far starting this decade. The first motivating example is the infamous Mirai Botnet that targets insecure IoT devices, mainly CCTV cameras and DVRs, routers and modems, but more alarmingly, it targets and adds more devices to its target list. Various new vulnerabilities, CVEs, 0 days being added to the arsenal and to various modifications of the Mirai Botnet. And everybody knows about Mirai Botnet. It's one of the classical playbooks to be used in the IoT cybersecurity presentations. But the main and core reasons about success of Mirai Botnet and why it's so scary is because it was basically targeting insecure firmware and insecure configurations of devices. There's a lot of technical and white papers, and I highly recommend this understanding the Mirai Botnet. But again, this is one of the main milestones in IoT cybersecurity awareness, where everybody started to become aware about insecurities of IoT devices. Then a couple of years ago, Vodafone discovers backdoors in Huawei equipment and firmware, which is basically a telecom, a critical infrastructure type of company. And these backdoors and security vulnerabilities pose a high risk to privacy of mobile phone users, internet users, as well as to critical infrastructure of various countries around the world. And again, these backdoors stem from the fact of these being implanted in the firmware for high-grade routers that are used throughout the telecom core network, and many times they are present also in the customer premise equipment or CPEs or modems and routers that are in residential homes. Then some more motivating example, in case you have missed it, the Argent 11, the cybersecurity vulnerabilities that were found in widely used third-party software that is then subsequently compiled and built into a large variety of devices, including medical devices, automotive devices, and critical infrastructure devices. So again, these are not particular backdoors, but these are vulnerabilities in a very popular third-party software. Therefore, the supply chain of IoT and of IoT solutions needs a little bit more caution. On similar line, we have Ripple 20, which is a series of zero-day vulnerabilities in widely used low-level TCP software library, and it is estimated to affect hundreds of millions of devices. This is pretty much similar to the Argent 11 in the sense that it's a set of serious vulnerabilities in some component that is used not necessarily in desktop computing software, but it is used in IoT or industrial control systems or industrial devices. More recently, on a similar line with Argent 11 and Ripple 20, Amnesia 33 is a set of 43 vulnerabilities which impact 4 open source TCP IP stacks. And if you're into the networking and network development, then you know the TCP IP stacks are the core of communication of any device, including or especially IoT devices. So the impact is really critical because it basically compromises the entire communication security and communication privacy of these components, and therefore of the devices that are built on top of these components. And moreover, it could also lead to remote code execution and other types of vulnerabilities, basically a complete compromise of the entire IoT ecosystem that builds on top of these components. So you can see that from Argent 11 to Ripple 20 to Amnesia 33, the number of vulnerabilities only just increases, and it is natural because the number of these components that maybe many of you haven't heard about until today, like micro IP and FNet and Pico TCP and NotNet. Basically, these are small footprint type of software libraries, whether they are open source or closed source. Their main intent is to be as low footprint as possible so that they can be installed in a variety of constrained and low resource devices. And therefore, these libraries, especially those which are commercial and closed source, they do not get so much scrutiny as the software and libraries that are widely used, for example, for desktop and server computing and tablets and so on and so forth. This number of vulnerabilities, the main point is that this number of vulnerabilities and third-party components being vulnerable will only increase because there are so many of them. They are just in the unknown. These are the tip of the iceberg, and the deeper we go to the base of the iceberg, the more vulnerabilities and the more vulnerable and exploitable third-party components will be there. Then more recently, if you have been following the CCTV camera or in general the video surveillance markets, the government warned on critical Hikvision flaw in CCTV cameras, and most likely if you've traveled around the world, you've entered into the visor of one of these Hikvision or Dahua type of cameras. They are very widespread. There are millions of them. And in this particular case, it was a 9.8 CVSS, so very critical vulnerability, literally compromising the entire network where this camera is plugged, and also the entire privacy of the video stream that it is supposed to keep private. Moreover, there is increasing concern about the security of these IoT devices, and in particular their firmware that are either not secure enough, or they have deliberate backdoors, or they have third-party components which are not verified, validated in any way. So there is a recent support and plan by FCC to actually ban the following vendors that have Hikvision, Huawei, ZTE, and Hytera. And basically the main point of FCC by putting this ban is that they don't longer provide security guarantees, and they undermine the national security of United States or its allies. So you can see that the importance of firmware security and the importance of IoT devices or embedded devices is increasingly important, and it reaches really high levels of discussion. FCC, Senate, and Congress discussing on these issues, and it will become even more important in the following months and years. So what is the common ground of all these motivating examples is that all these examples are tied together by three factors that multiply each other. So first is the presence of insecure, vulnerable, and exploitable components inside binary firmwares, and in particular vulnerabilities or insecurities in third-party supply chain, whether it's the supply chain partner or whether it's the supply chain component. This combination is basically one of the Achilles heel of IoT security, regardless of the vertical way it is being used, whether it's a telecom, energy, oil, gas, aviation, maritime sector, and so on. So let's step a little bit back and try to understand what is firmware in fact. Firmware is basically a software package meant generally for embedded IoT, industrial IoT devices. Its main intent is very much like software updates for desktop computers. And its name as firmware comes from historical reasons where it's a piece of software or a piece of ware which is not so soft, which is not so updatable, upgradable, or modifiable. Therefore, it's called firm. So it is supposed to stay quite static during its lifetime. And this term was coined much before IoT and industrial IoT. Therefore, those devices were not supposed to be connected to internet, receive a lot of patches, a lot of updates or features, or become feature-rich and expose various APIs, where nowadays they are literally connected to everything and expose rich and complex APIs. Therefore, they need a lot of malleability or possibility to modify themselves. So they are literally, the firmware becomes a software in the most traditional sense, that it is updated, modified, patched, and secured pretty much similar to what a modern desktop or server software is. However, compared to many of the desktop or server type of software, many times it is a black box binary blob, or it can be a set of binaries put together in a zip or in a file system format. But at the end of the day, it is just a black box because you can see that these security issues appear out of nowhere, backdoors, vulnerability, exploits, and so on and so forth. So there are generally two big categories of firmwares, and it's important that we touch a little bit on this to make a little bit of clarification. First, there is what is known the UEFI or EFI or older name BIOS firmware. Basically, this is also called a firmware, and it is a firmware which is usually put in a small chipset, which is called the BIOS chipset or UEFI chipset or TPM chipset. And its main functionality is to boot the board. In many cases, the motherboard of the PC or the GPU board or the software development board, such as Raspberry Pi or various other chipsets on boards. So again, their intent is to do basic input-output system or BIOS or their subsequent UEFI modifications. Optionally, and more recently, this type of BIOS firmware is used to establish root of trust and work with TPM and set hard disk and RAM encryption, decryption keys. So basically, all these functionalities are being basically every major ones. They have this support for root of trust, secure boot, and encrypted hard drive by default. So this comes normally from the boot time of UEFI firmware. Usually this is a piece of x86, at least in modern versions, modern motherboards, it's x86 type of code. It has a little bit of different architecture and way of doing things. It might have its own micro footprint operating system or not. And anyway, it's not our focus today, as I'll show on the next slide. But again, it's good to know that there this type of firmware term. So when you see firmware, it's good to understand what firmware you are talking about, whether it's UEFI firmware or general IoT or a device firmware. So this is the second category of firmware that we will be talking about today and what is our focus today. And it is the operating system plus application type of firmware. These are generally the type of firmware that operate the entire device end to end, whether it's a Raspberry Pi, whether it's ESP32, whether it's your router or a VoIP phone or a printer or avionics device. It's the type of firmware that we're talking about today, and we focus on at Binare. So these are the full-fledged operating system plus application type of firmware. They are pretty much similar to desktop operating systems such as Linux, Windows, macOS, and in fact, many times these IoT, industrial IoT type of firmwares, they are based on Linux derivatives or Linux variants, or maybe some other proprietary open source, closed source type of operating systems that are less known. Usually, these firmwares, they are not running or being designed around x86 code, which is predominant on desktop and server architectures. Many times it is ARM or MIPS or many other types of CPUs. So the analysis of that code is a little bit different than the traditional x86 security analysis. And the reason to discuss and to present this differentiation is because that different firmware types, they have different threat models and they require different analysis models, and that's really important to understand this difference, what we are talking about today. How these, it's also important in order to understand the security of these firmwares for IoT devices, it's important to understand how these firmware are created in the first place. So what is the most common method in order to understand their cybersecurity pitfalls and vulnerabilities? So normally they start from existing software development kits and operating systems, which rhetorical question could be vulnerable, could be obsolete or end of life. Then these software development kits and operating systems are being combined with third-party dependencies, which themselves can be vulnerable or maybe end of life or obsolete. And then on top of that, the vendor itself adds a vendor or device-specific changes or patches or applications or features. And basically, it has a complete firmware for operating end-to-end the device. On top of that, there's the complexity, which is sometimes optional, which is called white label rebranding, which means that there are device development companies which do not put a particular label on them. They just sell them as a white label, and then the big brands just put their own big brand label and market them as if they were their own creation. But what it means that it complicates a little bit the discovery of vulnerabilities and tracking them across the vendors, and it adds just a more complexity layer to vulnerability and exploit hunting. So again, after the creation, this creation method is applied, the result is still a black box binary blob, many times in a proprietary packaging format, and many times highly vulnerable, as we will see in a second. So there are a couple of challenges associated with these operating system plus types of firmware for IoT and industrial IoT devices. So for the vendor, the main challenge is from cybersecurity perspective is to understand what is inside the firmware that we release. Like, is the vendor 100% secure that they are not leaking any passwords or secret or private keys or putting some debug versions of their software? And what are the libraries they are actually pulling together into the final build? Then from device user or owner perspective, whether this user and owner is an end user individual or whether it's just their main concern or challenges is to understand what is inside the firmware that they are going to install on their fleet of routers or devices. Is it a firmware that is secure? Is it a firmware without backdoors, or maybe it contains backdoors, and how do we verify that? Does it prey on our privacy or the privacy of our users? So again, this is a challenge for device user and owner. And then finally, from device cybersecurity specialist, for example, the pen tester or cybersecurity consultant, the main challenge is to understand what is inside and what is vulnerable and exploitable in the firmware that they analyze. It's a black box binary. They have this firmware or device for analysis, and their question is to understand how can a potential attacker compromise it and how to understand what's inside that firmware. So some solutions to the above challenges is as follows. First, because the firmwares are many times in binary format, it requires binary analysis and reverse engineering. And this basically is required for a couple of reasons. First of all, by doing this, it allows the analysts to discover and map vulnerabilities that are inside the binary firmware. And then at the same time, it allows to recover the SBoM, or software bill of material. And I'll explain in the next slide what is SBoM. Then another, like an additional solution to some of the previous challenges is to do SBoM analysis and monitoring, basically analyzing the software bill of material, what are the third parties libraries inside there, what is their vulnerability exposure, and what is their attack surface and available exploits and their release timelines. And then finally, an additional solution is the presence or application of technical certifications, such as ETSI 303645. Again, we will show them towards some final slides. And these technical certifications can help basically certify, or at least certify to a certain degree, that the device have been, and the firmware in particular, have been exposed to a well-established methodology of cybersecurity testing, and that the vendor or some third party have performed some cybersecurity analysis before that firmware or device goes into the market or is being connected to a private or enterprise network. So first, I want to touch on the need for SBoM analysis and monitoring. So again, as I mentioned, SBoM comes as a software bills of material, and it is a list of all open source and third-party components present in a code base. So normally, this SBoM is created based on the source code. So it requires, for the start, to have a source code base, and from there, because the source code is present, it is more or less relatively easy to extract the software bill of material. Now, the rhetorical question is how to SBoM without source code. For example, when you have only the firmware binary or just the binary. So it becomes a challenge in itself to recover the SBoM when the source code is not available. And the source code could be unavailable for many reasons. For example, the telco company has a lot of routers in their networks, but they don't have the source code. They just receive the firmware updates from their suppliers and vendors. So how can they do a software bill of material and monitor the state of their router? So this is a tricky question. It requires quite some introspection and automation tools for that. So, however, the main point of software bill of materials is to help solve supply chain cybersecurity visibility, in the sense that it gives visibility what is inside a particular software that is being installed on a particular device, whether it's a desktop, server, router, printer, VoIP phone, or mobile smartphone. And information administration, NTIA. On SBoM, there is a lot of standardization and dissemination efforts regarding SBoM, which I heartily recommend to check. And why this is important? It is important because this SBoM is taking actually a very high level visibility recently. For example, there's a recent President Biden executive order on improving the nation's cybersecurity from May 2021. And for example, you will see that it will require that all of the software that goes into certain types of purchases, whether it's a software or firmware, will require to provide software bill of material for such products. Then, of course, it also requires that the vendor or the supplier will employ automated tools to maintain trusted source code supply and basically monitor. I would like to explain a little bit the need for binary firmware analysis and why it's needed. Well, there are many steps in many phases in the software development lifecycle and operational technology, starting from requirements to operations and monitoring and maintenance. Okay, 1 second. Appears to be some issue. Let me try again. Binare I/O is operating between the source code and the binary code that is running on the device, basically from the build stage until the firmware and binary is being deployed. Basically, I recommend to check our blog for more details about this infographic and lifecycle, software development lifecycle and operational technology lifecycle, and why every step is important. But I'll try to explain the importance of binary firmware analysis with two big misconceptions. First, the misconception number one is that, some companies say that we run source code analysis, we have 100% coverage. So the main problem with this misconception is that the IoT devices mainly run binary code. So there is no source code analysis to be performed there, right? Or if the source code analysis is performed, it still is performed on the source code, not on the binary, which is the actual thing that runs on the device. And the main problem with this is that the source to binary build process is prone to cybersecurity issues. It means that there could be compiler-induced bugs, there could be compromised builds and DevOps infrastructures, there could be internally, externally implanted vulnerabilities and backdoors, and also there could be misplaced crypto keys, secrets, super admin passwords that the vendor forgot to remove after testing, and so on and so forth. So the binary is actually the main thing that is important to be analyzed from a cybersecurity perspective. Of course, we are not saying that source code is not necessary to be performed. It is source code analysis is required, but it also requires the binary firmware. One doesn't exclude the other. The second misconception is that from our company is that they have live device monitoring, so they can detect 100% of attacks. Well, this is definitely good to have live device monitoring and protection. The main problem is that once the attack is happening, there are some vulnerabilities that attackers hunt for. So the question is, why not detect those vulnerabilities in the binary firmware before the attackers do, right in the first place? Why wait until the attack happened? So to put it in perspective, the live device monitoring and detection is reactive process. Usually it is quite or too late. However, it's still useful and is important to do monitoring and detection. On the opposite, binary firmware analysis is proactive in a way that is done before the firmware reaches the fleet of devices. And the most important is that it is cheaper and better to fix one firmware than to recall 100 million devices or chipset once the firmware is vulnerable firmware is running on those 100 million devices. So to conclude, this need for binary firmware analysis is that cybersecurity requires defense in depth, and definitely all of these items do not auto-exclude the others. So source code analysis is required as much as firmware and software binary code analysis is required, as much as SBomb recovery monitoring is required, and as much as code and device hardening is welcome, on top of live device monitoring. So all these defenses might help the cybersecurity of a successful IoT deployment and solution. And last but not least, it's, as I mentioned, the solution for technical challenges is that the technical certification can help all these stakeholders, such as device vendors, user and owners of the devices, and cybersecurity professionals to validate the firmware binaries that they're coming from supply chain partners, that the device owner can take an informed purchase decision whether a particular device is more cyber secure compared to some other from a competitor, and to help device cybersecurity specialists to know what has been tested and how, and what to focus on during a pen test analysis, certification, and validation. There are a wide range and growing range of IoT-specific cybersecurity certifications, such as ETSI 303-645. There is a typo. I'm sorry about this. UL 2900, IOXT Alliance. They're applicable to either generic IoT, generic scenarios, or they are specific to a particular field, such as telecoms, industrial IoT, or medical devices, or automotive. And at Binare, thanks to our analysis, we can definitely help bring companies closer to this certification at a fraction of the cost. Why investing so many 10,000s of euros just to discover that you are not even close to certification, when you can automate the whole process as much as possible and ensure that cybersecurity is good before even attempting the first certification. So let me quickly go to the live demo. At the same time, I try to check if, well, I'm not quite sure if the stream is still running on LinkedIn, but I hope it is. Let me quickly go to the demo. So, for example, here we have a demo instance. As I mentioned, we normally allow an upload of a particular device firmware to our system. Due to the time, I will skip this and will get directly to the results. As you can see, we have instances with thousands of firmwares already analyzed. These are real-life firmwares, not synthetic ones. So these are the firmwares that run on actual devices. And just to give you an idea, I'll go quickly to some particular URLs that show the type of analysis that we perform. So, for example, once a particular firmware, as you can see, this is a D-Link wireless network camera. Once we perform the binary reverse engineering and analysis, we have a particular number of files that we recover from that reverse engineering, and we identify software components, for example, 68 in this case, and we then map and discover the CVEs that are relevant to this particular firmware. So in total, there are about 2,000 vulnerabilities. About a third of them are high and critical, which is really bad. And then we also provide per component the cybersecurity and CVE posture. So it is pretty clear which components are more vulnerable and which components need to be addressed faster or sooner rather than later. We also provide other type of information based on CVE, CVSS, and CWE data. For example, if we go to the vulnerabilities tab, which is, for example, here, then we will provide the vulnerability and CVE, CVSS data, and CWE data associated with this in more detail, so that the analyst can go and explore each particular CVE or CWE. And for example, if they are interested in CWE 119, which is also the highest bar here, which is normally the buffer overflow, for example, they can filter for CWE 119, and they can see that there are about 200 vulnerabilities that are related to buffer overflows, so that the person who is responsible for buffer overflow exploitation, pen testing, or fixing them, they can take a look at each individual ones and then check their exact details. So in this particular case, this CVE is applicable to OpenSSL. Therefore, it basically shows that it's really required, or maybe it's recommended, that this OpenSSL version should be replaced or upgraded or completely removed, and some other SSL TLS library to be used instead. we can clear this CWE, and then we can apply other types of filtering. For example, if we take the vulnerabilities that are have the high scores, then they can basically play around with the particular scoring and focus on what is really important for the team, whether it's the pen test team or the developer team. We also, as I mentioned, we basically do the software component analysis, and this software component analysis basically is tightly related to the software bill of materials, or SBoM, as I mentioned. So once we do a particular analysis of a firmware, we create an SBoM. In this particular case, you can see this is a DSR, again, a D-Link firmware, which has these components with this particular number of each component. And then we basically create a set of reports that show the vulnerability posture of this particular SBoM. So there are two things. The firmware analysis is one thing. It contains software component analysis, vulnerability analysis, and some other types of analysis of vulnerabilities or usernames and passwords. The SBoM is only focusing around the SBoM vulnerabilities. So in this type of report, again, similar type of information is being presented. It's just presented from SBoM perspective in a slightly different format, which is a dynamic HTML. And it's possible to go and play with this HTML as pleasing. So it's possible to see more information about each of the affected component, their scores, and then each CVE that has a particular score, and see more references and the products that are affected, or components that are affected. So basically, it's a SBoM focused component, and again, this SBoM we are monitoring for new vulnerabilities, and every time new vulnerabilities that appear to existing components, we create a new report. So you can see that the subsequent reports have less entries in the vulnerabilities because they are a delta type of report. So this report contains only some new vulnerabilities related to existing components. And in this case, we can see which are these. So we see that the Linux kernel added 7 new CVEs with the highest score of 7.2, pretty high. And it added these 7 vulnerabilities during August 2021. So this helps to keep a track or an eye on the existing components that are inside the firmware that were once, for example, thought to be secure. We also, as I mentioned, we analyze for other types of artifacts and cybersecurity problems. For example, this is a Linksys router. We can check the usernames and passwords. In this particular case, there is no hash password, but we've detected. Maybe it's good to check whether the list of users are according to vendor expectation. However, some other examples include users and passwords that contain, for example, the hashes. In this particular case, there's a firewall entry which contains a pretty weak MD5 crypt hash. And which is not maybe so secure anymore. And also we can detect various other scripts that inject user password entries into etc password, for example. Similarly, we analyze the crypto material, such as private keys. For example, if we want to see all the private keys, we see that there are private keys present. And this server PM contains a private key, so we can check more details what it is about, and we can see that it is a private key related to the self-signed certificate of this particular router and device. So this again can be used to detect the insecure storage of private keys or leaking SSH or other type of private keys and secrets that are not intended or shouldn't be in the firmware. So this is a really quick overview of the analysis. Again, we are adding more and more analysis all the time. This is just a quick demo. I don't want to focus extremely a lot of time right now on the demo. But again, the idea was to introduce the firmware, the need for binary firmware analysis, the challenges with the firmware security analysis and with IoT devices. And with this, I would also, the Binare team would like to take the opportunity to initiate the Firmware Security Day, 1st of November. Why? Well, October is the cybersecurity month and it just ended. And why not take one extra step, one extra effort and do a Firmware Security Day 1.11 and declare the 1.11 to 7.11 Firmware Security Week. And this is what we propose and initiate. We will be releasing some awareness materials on our channel, so please stay tuned. And firmware security is a must-have. And what do we want to achieve with this Firmware Security Day 1.11 and Firmware Security Week 1.11, 7.11 is first of all to encourage everyone in the industry, everyone in our followers, everyone in your networks to check the firmware that is fully updated across your devices or fleets of devices. Just take a day, take a week to focus on that particular firmware security problem and perform firmware security analysis and check firmware that the firmware is secured for each of the devices that you are actively using. And then the main thing is to raise awareness across users and stakeholders, whether it's stakeholders involved in a software development lifecycle or information technology or operational technology part of the IoT, and raise their awareness about not just cybersecurity, but the firmware security itself. And last but not least, try to follow Binare.io for firmware security and IoT security awareness materials at the following links. After this webinar, we will be releasing some really interesting materials related to this Firmware Security Day. And we will try to encourage all our audience and everyone in our networks to be more aware about the importance of firmware security and to make the IoT devices more secure as we move forward, because this is our mission at Binare team, at Binare.io. Our mission is to help secure the billions of devices around the world. So thank you so much for your attention, everyone, whether joining from Zoom or LinkedIn Live, wherever you are around the globe. Thanks for your time checking our webinar. Please go and try out yourself our demo, or if you need more guidance on how to use our demo more effectively, or you just want to talk, we are happy to hear from you at hello@binare.io. And once again, myself and entire Binare team would like to thank you for this opportunity to showcase this webinar and to get in touch with you. And until next webinar, please stay safe and keep your IoT devices secure. Thank you so much, everyone.